2D textures are a matrix of data elements storing colours for pixels, with some textures storing a 3D vector for normal mapping. Direct 3D uses a texture coordinate system of a U-axis that is horizontal and a V-axis that is vertical. These values are normalised no matter the texture size to being from 0 to 1. You can see the UV coordinates being set for the cube here and for the terrain down here. For each 3D triangle we need to define the corresponding triangle on the texture to map to it. You can see here in the default HLSL the texture coordinates being linearly interpolated across the triangle, giving every point on the triangle a corresponding texture coordinate. This has been implemented by adding a pair of texture coordinates to the vertex structure, so every 3D triangle defined by the 3 vertices also defines a 2D triangle in texture space. Textures are loaded in using the DDS texture loader CPP here, and they're created by making a texture struct here in the d3d util header. Texture resources are then set up here in the text waves app. For instance, the grass terrain texture is set up here. After this, an SRV descriptor heap is created, with 3 descriptors for either CBV, SRV or UAV that are visible to shaders. After this, the SRV descriptor is described here using a d3d12 shader resource view desk object, which describes how the resource is used, as well as information like format, dimensions, and bitmap counts. Textures are then bound to the pipeline here in the draw render items method, with the text resource being bound to the 0 slot parameter in the command list as a shader resource view descriptor table. Magnification is when a texture must be interpolated to a higher resolution. For example, when a texture fills the entire screen like this, where texture resolution is less than the screen resolution. There's 2 ways of doing magnification, either by constant interpolation or linear interpolation, which is one that's almost always used. Neither solution though is as good as high resolution texture data. Some games even try to stop you from getting the camera too close to a surface to help minimise the problem. Minification is opposite of magnification, where the text resolution is higher than the amount of pixels the texture covers on the screen. Interpolation is still used for this, as texture coordinates for pixels won't coincide. However, there's a technique called mip mapping, where a texture is downsampled at initialization time to smaller versions of its texture, creating a mip-map chain from the highest resolution to the lowest. This, at the cost of some extra memory, allows a better approximation of the screen geometry resolution by choosing the nearest mip-map level to match applying interpolation as needed. There's also linear filtering, where the 2 closest MIP levels to the screen resolution have constant or linear filtering applied to them to use a texture colour for each, which are then interpolated, which you can see here with a blend of different colour patterns that I have applied to the different MIP levels. You can see the MIP levels and the most detailed MIP in the SRV descriptor here. You might want to reduce the most detailed MIP to save on resources in some games. You can also see the MIP LOD BIOS in some of the sampler states. Direct 3D allows us to use address modes to alter how texture UVs are maps. You can see the sampler states for the address modes here, and the registers here. To make it easier to see the different address modes, I've scaled all textures down by 2 here. The first address mode I'll show is linear wrap, which repeats the image at every instance point. This is the most common mode and can be used to tile surfaces, increasing the text resolution without supplying additional data. The grass texture is tiled in this solution and is scaled by 5 to tile it 5 by 5 across the land mesh surface. Next is the mirror address mode, which mirrors the image at every integer junction. I've used an anisotropic filter on this mode instead of linear, which helps to alleviate the distortion that occurs when the angle between a polygon's normal vector and the camera's look is wide. This address mode is called border colour, which maps every UV not in the 0 to 1 range to a specified colour, in this case white. This last address mode is called clamp, which maps each UV not in the 0 to 1 range to the colour T, U0, V0, where U0, V0 is the nearest point to the UV contained in the 0 to 1 range. To animate the water, the texture coordinates are translated as a function of time in the animated materials method here, which is called every update cycle. We can see the offset vector being calculated and the texture matrix being set. Because displacement is very small for every frame, it gives the illusion of a smooth animation, and the use of the wrap address mode makes this texture seamless.